This is 2.1 Rates of Change and Limits, Part 2. Your objectives for this lesson are to apply properties of limits and to find limits analytically and graphically. So starting off, we already know, and we looked at this briefly last lesson, if you have a constant function, k, y equals k, then your limit as x approaches c will be that constant k. And then if you have another function, y equals x, that is your identity function, as x approaches c, the limit of that function is c. So these are some important rules to keep in mind as we look at this next page. Okay, let's cover a bit of this up. Your properties of limits, this is page 58 in your textbook. There are a lot of properties of limits listed here, but they're not too difficult to remember, so don't let the long list overwhelm you. If L, M, C, and K are real numbers, and the limit of f of x as x approaches c equals L, and the limit of g of x as x approaches c is m, then we get the following properties. First up, the sum rule. If you take those two functions that we were talking about, f of x and g of x, and you want to find the limit of their sum, f of x plus g of x, as x approaches c, so notice that this is the same as up here, then the limit is just the sum of the limits of these functions. So L and M, L plus M. Notice plus sign here, plus sign there. So pretty easy. Your difference rule is the same idea but with subtraction. So if you take the limit of f of x minus g of x as x approaches c, then your limit is just L minus M. So the limit of the first function as x approaches c minus the limit of the second function as x approaches c. And again, so we have a minus here, minus here. The product rule. If you take the limit as x approaches c of f of x times, so times g of x, then you get the limit of f of x as x approaches c, that's your L, times m, which again is the limit of the second one, times. Okay, the constant multiple rule. We have the limit of k, and k here is a constant number, so k is a constant, times f of x, so that was one of our functions, and we're taking the limit as x approaches c. This turns out to be just k, so k from here, times the limit of that function, which is L. And if you remember, if you look back to those rules that we talked about at the beginning of this, the limit of a constant function is the constant. So it's the limit of this first part, the limit of this is this, times the limit of this function, f of x, which is the L. So this is pretty similar to the product rule. It's just with a constant. So this is with a specific function instead of a general function, f of x or g of x. Okay. Now the quotient rule. Quotient, remember, is with division. So if you have your first function divided by your second function, you're taking the limit of their quotient, then that is just the limit of the first one divided by the limit of the second one. Please keep in mind that you can only do this when that second function's limit is not equal to 0, because again, you cannot divide by 0, so this part is important. If this did equal 0, then your limit would be undefined. It would not exist. Okay. And the power rule. This is our last one for right now. The power rule says that if r and s are integers and s is not equal to 0, then the limit as x tends to c of the function f of x to the power of r divided by s. So this is why s can't be 0, because we have r divided by s. And whenever you have something in the denominator, it cannot be equal to 0. So the limit of this is L, which remember was the limit of f of x as x tends to c, to the power of r divided by s. So basically you just take this part here that you already know the limit of, that L, and raise it to this power, so that little extra bit. And this will work as long as L to the r divided by s is a real number. Okay, example 1. Use the observations, the limit as x tends to c of k equals k, and the limit as x tends to c of x equals c, and the properties of limits to find the following limits. So basically we're using what we talked about on the first 2 slides to solve a couple problems. Our first problem here, we want to know the limit as x tends to c of x cubed plus 4x squared minus 3. And what I notice here are we have a plus sign and a minus sign. So we're going to use sum and difference rules. Sum and difference rules to break this up. So this is going to be the limit of x tends to c of x cubed plus the limit as x tends to c of 4x squared minus the limit as x tends to c of 3. And from here, we want to actually find the limits. So remember that if, and this is this first part here, if you have the limit of x as x tends to c, that equals c. Basically, you took this c and you plugged it in for the x, and out pops a c. So we're going to do the same thing down here. We're going to take this c and put it in x's place. So this is, sorry, I'm starting to write limit. This is just c cubed plus, same thing here, we have another x. So put the c here. And we have 4 times c squared. Now here there is no x. This is a constant, so we're looking at that k from up here. This is our k. And the limit of a constant is the constant. So instead of a c, we write minus 3. The minus sign is from here. The 3 is the constant. So looking at this, I cannot simplify this anymore. So this is our answer. That's the limit. Part B. We're going to do the same thing. So I want to break this up and then find the limit of each individual term. I see some plus signs, minus signs, so that tells me sum and difference rules. I also have a division bar, so I'm going to use the quotient rule here. Okay, so this is equal to the limit as x tends to c of x to the 4th plus the limit as x tends to c of x squared minus the limit as x tends to c of 1 all over the limit as x tends to c of x squared plus the limit x tends to c of 5. Okay. And again, plugging in, we have c to the 4th plus c squared. You put a c there because there is an x, minus no x, so I'm going to write 1 over c squared plus 5. And since I do have some division going on here, I want to look really quickly, see if I can factor and cancel. I cannot factor the denominator looking at that quickly, so I'm just going to circle this. That's the answer. Okay, let's cover some of this up. Now we're going to talk about polynomial and rational functions. So this is a theorem in your book on page 59. And you can see your first part of this. So if f of x equals this polynomial function here, so a sub n times x to the n plus a sub n minus 1, x to the n minus 1, and so on, if that is a polynomial function and c is any real number, then the limit of the polynomial function, so we have f of x here and here, so the limit of the polynomial function is equal to f of c, which is equal to this polynomial here. So again, just like before, you're substituting in the x's with c's. All that happened between here and here was you changed x to a c. So that is x tends to c, change x to c. And the second part of this, if f of x and g of x are polynomials and c is any real number, then the limit as x tends to c of g of x over f of x equals f of c over g of c. So the long polynomial is not written out here, but it's the same idea. Change x to c. And again, g of c cannot be equal to 0 because you cannot divide by 0.